Yeah, so I'm a roboticist. So today we will talk a little bit more about the technology side and what I understand what you did the last couple of weeks or so. And yeah, the idea is that first I tell you like real quick about a little bit of the research going on in my lab. And then I will turn into a more like kind of lecture style where I try to like what I believe is like the most important like textbook style things to learn here. I will try to stay within like 60 minutes or so to give us quite some time for questions. So many of the things that I'm going to talk about will be a bit shallow. So if you're interested, then you maybe want to like note some question and then feel free to ask it later. So hopefully we can also do this in a quite interactive style then like towards the end. But if like something is really out of order in between, you can also of course stop me anytime if otherwise you don't really understand what this is about. So first, yeah, I'm from the University of Konstanz in the far south of this country. So just this is the typical photo. This is how it looks every day, of course. Very beautiful if you haven't seen it. Next to the Swiss border, actually, like what you see in the left part of this picture is already Switzerland. For orientation, in case you are not so much familiar with German geography, this is where it is. Beautiful place. Make sure you see it at least at some time. Good. So my research is like traditionally since many years I do swarm robotics, and whenever I talk about robots, I'm referring to mobile robots. And because it's swarm, of course, we try to have many of them, whatever that means in any case. Then, of course, AI, or more properly addressed machine learning nowadays is unavoidable. So we do that. We also do a little bit of reinforcement learning, but also this other method you might have stumbled over at some point called evolutionary computation. And then we also do some more fancy things and maybe partially also a bit odd. So this is what we call biohybrid systems, where we try to bring like any form of technology and like natural organisms together. These organisms could just be humans, right? So for a roboticist, a human is already a particular, interesting, strange animal. And but we also work with natural plants, but that's something I will not really talk about today, at least on my slides, but I understand some of you in the Journal Club looked into that and I never responded to your requests, so sorry about that. Now you can punish me with all your questions if you want about plants, but I have nothing on the slides about that. This is my fantastic team. These people keep me busy every day, and then I'm also co-advising David himself, and Mosen is also here. And yeah, it's just great to do this work in such a team, obviously. And this is, you know, these people do the real work. I'm just traveling around and telling people about it, I guess. Good. We also have this kind of robot zoo in my lab. Just a number of different robots, basically from like small to big, not really to scale. So you might have seen this tiny kilobot somewhere, which has a footprint of a €2 coin. Oh, I'm not supposed to move around. The Themio robot, you also see that in a like kind of cyborg, specially adapted way here in these labs. The Limo is a new Chinese robot, and then this big black robot is the Turtlebot 4, designed for education. It has a LiDAR, like a laser scanner, an RGBD camera, and with that you can already do like kind of state-of-the-art methods. So something like SLAM, for example, this would be simultaneous localization and mapping, a standard thing in robotics. And this is the Jekyll robot from ClearPath Robotics in Canada. This is already a bigger robot. It can also go a little bit off-road, 17 kilos, and this could also move around on campus also. I mean, I'm not sure what your campus really looks like, but more traditional campus maybe. Good, and then as you might know, for the papers that we submit, usually we have to also have a a video with it. That's a tradition in robotics by now. This is just like a kind of more or less random, not random selection of such videos, just to kind of overwhelm you and just, you know, give you this big, fast message that I like it whenever there's many robots, and most of these videos are sped up. So, you know, it already looks a bit like, for me at least, as ants or so that move around and do things. Most of these robots can't really do much, right? It's these kind of like toy robots that we use in the lab, maybe with the exception of the Jekyll robot. And this is also, this is, for example, Mosen's work here from Berlin. The other things are, if I'm not mistaken, this is also with colleagues in Brussels, for example. But you get the idea, right? So these robots, sometimes they can like do things to the environment. Like the robots on the top left, for example, they're actually braiding something. Otherwise, it's just robots moving around, and it's more like a proof of concept of more basic algorithms that we try to prove that they actually are in touch with reality and do work. So then again here, work by Mosen and David from Berlin. Then on the top left again, these Jekyll robots. And here in the big picture, you see a facility we have in Konstanz, the so-called imaging hangar, like 15 by 15 meters, 8 meters high, a big volume with like the finest tracking you can possibly get for money. And then we have, for example, these 15 turtle bots that we can move around in this space quite comfortably and do like bigger scale experiments, and maybe sometimes also mix these robots with humans, which is then of course also super interesting. I told you shallow, it will not stay that shallow, but for now, you know, I just want to give you like a few videos here to get a quick idea of what we're talking about. And then because after a couple of years, I got a bit bored by all these toy robots, right? So we do everything in the lab, and then whenever you present that to people, you have to make claims like, yeah, you know, this is basic research, we show it on the robots, but at some day you could do something useful out there. So I thought like, okay, now I'm in Konstanz since 2.5 years next to this beautiful lake. So maybe looking into something like an autonomous boat, and why not an autonomous sailboat? This is a model that we just bought off the shelf. This is an RC sailboat model, something you can actually buy. And we made this autonomous. So we pulled out all the electronics that was there, and then put in our own electronics to make this boat basically autonomous. And the fun part about sailing, not sure how much you know about sailing, I'm also relatively new to this, but the fun part for a roboticist is that the fastest connection between 2 points A and B is not a line, right? It's more, depending on the wind, you need to tack and actually plan a bit like how you want to navigate. So for that, I'm not supposed to move. This points of sail here to give you some idea, right? So if there's the wind coming from top, then you need to think about how to position your sail. And of course, you cannot really go against the wind, but you can tack, which means in like shorter angles towards the wind is still possible. And so on the left, you see, well, in first place, Pranav, the PhD student who is designing this boat from scratch. So now we have 2 boats, right? So this RC model off the shelf, and this other bigger boat, which is actually full carbon fiber. We are very proud of that because I think every sailor dreams of a full carbon boat. So we can actually make our facilities do that for us. And this is something like, I guess, 1 meter long, and then with the high sail that we have now, it's almost like keel to tip of the mast. It's like 2 meters or so. So already quite a size. It also has a thruster. Otherwise, like from a robotics point of view, it's a quite simple robot actually. So you have a servo, like an electric motor for the sail, and you have a motor for the rudder. Then you have a wind sensor, maybe a GPS, and you can already do something, right? That's quite nice. And because we do smart robotics, we of course also would want to build several of these, but for now we have one, right? It already kept Pranav busy for quite a while. So here you saw that I lied to you. This is how it looks like in fall time, right? So there is some fog sometimes, and like if you visit us, then better do it in summer. And this was like almost like one of the first tries when we put the boat into water, so still not everything was completely waterproof. That's of course one of my biggest fears, that at someday Pranav will come back to my office and it's like, oopsie, we lost the boat, right? This could of course happen once you go out of the lab, but it's also, it comes with a lot of challenges, right? So it's really interesting to do this kind of research because you really deal with the dynamic world out there, and our boat still only has like partial information, right? It doesn't have the perfect sensors to really perceive everything in any scene, which means then we're on, not yet on par, but we have the same challenge as these animals you've been talking about, right? So they evolve to deal with the real world. Once we want to have robots that do the same, it's really a challenge for us, right? So a little bit more about that, but most of the things will be a little bit more basic. So if you're interested, ask me later about the boat. Then, sorry, it's kind of unavoidable to mention my book, right? And it's, of course, the best book on robotics, swarm robotics, I should say, because it's the only book on swarm robotics that's out there. And currently, I'm keeping myself busy with the second edition of it. So if you have ideas, let me know what I should put in there. And I'm going really crazy right now. So by now I have 764 references in this book, which is insane. So memo to you, never write a book. It doesn't pay off. It just steals your time. Don't do this. Good. So the outline is a bit like this. So I understand that you have a lot of knowledge already about biology and collective behavior in animals. So let's think a little bit today about what can you do with that knowledge, and can it inspire you to build hopefully very intelligent robots that operate as a swarm, as a team, or in larger numbers. So first I will show you a few definitions of swarm robotics. Even before that, actually, I will try to give you a quick understanding, in case you have no background in robotics whatsoever, to give you a little bit a taste of the challenge that we face. And then I want to quickly mention, like, what does it really mean? Like, how can biology inform engineering in the end to do useful things? And then we go relatively quickly through these three like case studies or examples: division of labor or task allocation, collective motion, and then something like somewhat surprising, which is called less is more. In the end, because I thought you might be curious, we can also talk a little bit about where could this be going? Like, what's the future of swarm robotics? Is it a good one, or what are we going to expect? So real quick, if you need to design a robot, and I'm really coming from the software side, so, right? So by training, I'm a computer scientist, so I'm not, I mean, now we're building this boat. I mean, Pranav is building this boat for me, but I really don't know too much about hardware. So what keeps me busy is to this challenge, like, what can we do to make these robots intelligent, right? So to behave in good ways, clever ways at any time. But you start really, really simple. And so if you're really like fully naive about robots, and you've never really thought about too much, like, what can they perceive, and then what's challenging for like standard mobile robot, we should really start low, right? Because it's so easy as human beings, you have all this luxury of sensory input, right? If you're a healthy human being, you have stereo vision, you can smell, you have tactile sensing, you can hear very well usually, and you have all this sensor input, plus also like a really great brain, highly cognitive, that informs you very well in most of the situations where you are, what you currently see, and to make sense of the world around you. Our robots basically come with nothing in the first place, and then we can put a few sensors on it. So you should really think of these robots as a bit like what they look like. So this like tin can thing, and then you poke some holes into it. So it has like a little bit of an idea of what's out there. But that's pretty much it, right? And the better way of thinking about it is maybe like what makes you walk, like if you wake up in the middle of the night in your room, and then you get up from bed and you try to find the door of your room. Like what helps you doing that? Right, and then if you're not just moved in, or you're in a room you've never seen before, lucky you, then you might subconsciously maybe count steps or something like that. Is muscle memory that tells you how to get to your door, even if it's completely dark and you see nothing, right? And this in robotics we would call that autometry. So you can try to achieve something, like you can navigate even without sensor input, right? But maybe depending on like for how long you live there, you might also like go for tactile input and go along the wall, already some sensing, right? Or you might actually be able to turn on the light or use the flashlight of your phone or so. But yeah, really think of like in the beginning, the robot knows pretty much nothing, and then we give it a few sensors. In small robotics, often these sensors don't have vision, right? It's just some proximity sensing that can measure distances and so on. So it's really difficult with this little sensing to still behave intelligently, not running into things and coming up with great plans of what to do next. So on a more like systematic level, we can think about it a bit like this. So not super clear from this picture, but your mobile robot is embedded into the environment, right? So this is different from your laptop or like ChatGPT or so on. These are systems that are just sitting there waiting for input. Our robots are situated, they're here and in the physical world, and whenever the robot senses something, and then some magic happens and it comes up with actuation commands, it will move, and that will also change its next sensing, right? So there's a permanent iteration over moving, having new perceptions, deciding what to do next, and also the world might be dynamic and everything around the robot maybe moves, right? So to fill in this like magic part in the middle a bit, you could think very simple and you say like, okay, I do maybe a lookup table, right? So I try to enumerate all possible sensory input that this robot could ever experience. And maybe there's also like some internal state so that the robot can at least count or remember what happened last. And you map that just like statically, like in a telephone book to actions, right? Seems like it could be an option, but this would be actually a big book, right? So a big table, and sounds also very static. This robot would never learn, and like how much can you really achieve in this way? So like more modern takes in robotics would rather look like this. So the robot might have a goal that could also change every day or so. And it also usually has what we call a world model, which is a big word, right? Don't think Google Maps or something like an actual model of the world. It could be just this internal state where the robot can count, or it could actually be a map, but maybe just of this floor, things like that, right? And I can always ask you, like, where are you right now, or what do you think? How did you get in here, and what do you think? How do you get out of this building? And you will have some mental picture of that. For our robots, we have to program them into them, right? So it's nothing we get for free. We have to make sure that the robots actually can estimate where they are, that they can like produce actually a map. So this is all hard, right? So it sounds like I'm complaining about how hard my job is, but just because humans are very jumpy in assuming, like watching a robot and then you assume, at least subconsciously, that this robot probably can navigate the world as you can, right? But it's not like that in any sense. So this would be like virtually state of the art, that this robot then maybe can do some learning, maybe can do some planning, And in swarm robotics, we want to keep things rather simple, right? So maybe you have already seen some behavioral models of social insects or so, where the behavior is usually more on the reactive side. So very simple. And that's kind of like let's say the dream of swarm robotics. Like if you build really simple robots that are not very capable, right? So they don't have so many sensors, maybe they don't have much compute, and they have a very simple software running, like a reactive behavior that just react to whatever they perceive right now. Can they maybe, by working together, like an ant colony or a flock of birds, can they still do something awesome, right? And for an engineer, that's actually really a beautiful dream, because that would actually make my job easy, right? So I design something like the single entity, one robot, that would be simple. It doesn't have many sensors. It doesn't need much code for programming it. But then once I put them together in a room, whatever, then they do something awesome, right? That would be nice. The only problem is, in this world, very rarely there's anything for free. So the complexity arises once you have to make these robots to work together, right? But you're in the perfect place to think about that, right? So you know how animals solve this problem to some extent by now. So we could try to get inspired from biology and understand, like, okay, and these animals are not always really simple, right? So there's nobody in the world that can build an ant that can do everything that an ant can do. But maybe you can still learn from these animals, right? So just to show you like where swarm robotics is nowadays. So this is a random YouTube video, obviously. So there's, of course, these famous, by now, Amazon warehouses where the whole shelves move around, and they have hundreds of robots in one facility. Really amazing work, of course, making it just a little bit easier for these people to do the pick and pack. So they don't have to walk for so long, but still, I guess it's not a very enjoyable job. And so this is already out there, right? And is this swarm robotics? Well, we haven't defined it yet. So the question is like, is this centrally organized? Is there like one server pre-computing everything and doing everything ahead of time, maybe? Or what controls these robots? This is another example. This is a swarm of 100 drones, and now you can of course argue like 100 drones. Come on, there's these light shows with maybe 1,000 or thousands of drones. So this is Gabor from Budapest, and they actually control. So you can barely see them, right? But each dot here is a drone. And they have implemented a fully decentralized approach to organize the traffic of these drones up in the air. So there's not a central entity that's collecting all the information and then sending commands to everybody. It's every drone by themselves, right? And then they can still organize traffic and do something useful. And this is from our own work in our imaging hangar. This is now just 6 of these turtlebots. This was just a tiny demo to show also with a tracking system that you can actually have a human interacting directly with these robots. And so it feels a bit like walking with ducklings or so. You immediately feel the power, right? So they follow you everywhere, and so that's a nice feeling somehow. But this is just pointing you to what could be future ideas of what these robots could possibly do, and human swarm interaction is definitely something interesting. I mean, it would need a little bit more than that, obviously, but just to show you some and give you some idea of where this might be going. Okay, so let's look into the textbook, right? So what's really the definition of swarm robotics? And like one of the big shots there is, for example, Marco Dorigo. And then a couple of, something like 20 years ago, he wrote this. So I will just quickly read that. Swarm robotics is the study of how a large number of relatively simple physically embodied agents, that's just a fancy way of not saying robots, can be designed such that the desired collective behavior emerges from the local interactions among agents and between the agents and the environment. And this could already ring a bell for you, right? So because this also applies in parts to biological systems. And I told you about the idea, like we want to have simple robots, but then many of them in the hope that like something happens in the interaction part. Like once they can do something together, they cooperate, they collaborate, then maybe they can still do complex tasks that otherwise just like one really complex, expensive robot could do. And then there's also a definition, in this case by Benny, about the properties of robot swarms. So this is decentralized control. That's hopefully clear by now. So instead of having one entity, which also could be a single point of failure that does all the processing and then sending out commands, you do it in a fully distributed way, and there's like full autonomy in each robot. But by communication, they try to coordinate. Also, lack of synchronicity. This is what we do not all the time think about, that there's no global clock, which is actually also can be an issue for these robots, that they cannot just agree, like, let's meet at 2 p.m. because they don't share a clock, right? So you would need to explicitly make them synchronize, and maybe you've seen something like fireflies synchronizing or so we could maybe also work on collective models of collective behavior there. They're identical or quasi-identical. So this is the idea of mass production, point 4. That, of course, once you build simple robots, you could maybe mass produce them. Mathematically, they would still not be identical, but basically yes. And then you could maybe have, for cheap price, very, very many. And does this look like natural collective systems? So I would say yes, right? I mean, mass-produced, okay. But everything else these are not like big requirements or something where it would make it difficult for you to think of an animal swarm, right? That qualifies for these properties. I hope you see that. You could, of course, still ask, yeah, but what is this really good for? And why would you like go through the pains of working only in a decentralized way? That means each robot only has local information. Nobody has really access to the global picture. This sounds like, you know, it's making things hard, maybe unnecessarily hard. So there's, according to textbooks, there's usually these 3 advantages mentioned. So for example, robustness, right? Because all the robots are the same, you have a highly redundant system. So whenever one robot or a certain percentage of robots fail, the swarm should still be effective. Maybe it takes them a bit longer to finish their job, but it will not just break, right? Try that with your smartphone, like remove one component from your smartphone. In most cases, it will just break. Scalability, that's the idea that you can use the same algorithms, control algorithms, for virtually any number of robots. So usually we think about scaling up, right? So can you like, test your program for 10 robots, but then it also runs with 100 and 1,000 robots. But you could also scale down, right? So you test it for 100 robots, and then does it also run for 3? That would be scalability, like system size scalability. I'm very enthusiastic about that, actually. You can try to model that and predict, and that's can be a lot of fun. And then the third one is maybe not so convincing. This is flexibility. If you have these identical swarm members, there's no specialization in terms of hardware, which also then means like any robot can jump in at any time to like finish whatever someone else left as an unfinished job. So let's think about like how can biology really help us in engineering these robots. And there's, of course, I would say, but I'm ready to discuss, a fundamental difference between like how biology works or how everyday life of a biologist looks like and what we do usually in engineering. And in biology, I would say everything is a bit more top-down in terms of like what's there and how your understanding process works, right? It's a natural science. So they are exposed to all this like insane complexity of the biological world, and then they try to make sense and not necessarily reductionism, but they try to like look into the parts, and you would come up with an animal with a behavioral model of one ant, and then try to make sense of the behavior of the colony, right? So it's always like you start from the complex system and then you try to get into the details. While in engineering, you know, at least in robotics, the like computer science half of robotics is still has this mathematical origin. So we would start usually from scratch, like from a blank sheet of paper, and then design something, and then work our way up, right? So we start from nothing, and then we like create our own little complexity, and then we analyze whatever swarm behavior we get in the robots. And this is actually still a challenge, right? So we have these robots, and then we would still not be able always to predict how they will really behave once they work together, or actually don't work so much to work together. And then the other thing I want to clarify is these two ways of how you can do this. So there's bio-mimicry, which is the maybe more naive approach, where you would say, oh, these animals are awesome, right? I want to have such an animal. That means you go to the lab, and then you basically build a little Frankenstein robot that looks like an animal and mechanically works like an animal, in the hope that by directly copying it, you get something awesome on the same level. Of course, it's not something stupid, so that's still valid to do, but it's not always the best thing, right? So we have other means sometimes in engineered system. For example, for communication, why not using radio, right? Like, if you have it, use it. So this would be then this other idea that you can still work in a bio-inspired way, but on a slightly more abstract level. So maybe we would try to extract general paradigms and like general design principles from biology, and then implement them in a slightly more abstract layer into your robots, right? And this is just a symbol here that a quad rotor can still have software that is inspired by collective decision making in ants, right? But it doesn't look like an ant. And one more thing, but I'm only touching that here quickly. We might have a lack of shared goals. Of course, you can program goals into your robots, but in an ant colony, they don't share all their genes, but it looks like they're happy to like sacrifice themselves for the colony and so on. Actually a bit like a tricky subject in biology, but they usually share a goal, right? We can program our robots to share a goal, but imagine you have a situation in a warehouse where there's like different manufacturers of robots, and then who knows if they really work on the same objective at all times. So this might create issues that you don't really see in biology. Good. So maybe now it's time to go through these 3 examples. And I want to start with this first one, which is task allocation. You can only make sense of this slide if you know that this, what is it? No, it's not BBC, it's some UK series. Have you seen Taskmaster? Is that a thing? Okay. Yeah. So I got a bit like carried away during COVID by killing time watching these YouTube videos. And sometimes I really find it fascinating, like looking at it like I mean, I'm not a psychologist, right? But in terms of like how do they allocate tasks, and this, if you remember this one, this was actually where they really did a bad job in allocating who should be doing what and succeeding as a team. So this is the problem also sometimes for animals, and then also, of course, for our swarm robots. So let's have a quick look into how task allocation works. So this refers to a process where individuals, so either animals or robots, are supposed to distribute work or jobs among themselves. And we usually do that in a dynamical way, so it's not like offline pre-coded or so. The robots would like be deployed, and then they face a certain situation now in this environment, and then they should find out like, okay, maybe we need so and so many on task A and so many on task B. Again, with without centralized control, right? So they have to decide that by themselves with this like partial information. They don't see the big picture. This actually includes a few other things that are also relatively well defined in biology. So that there's a division of labor, which would be the idea, like almost a precondition that you actually allow individuals to specialize, or at least that they at certain times do different tasks. And then task partitioning is the idea that like a general task, like maybe foraging, can be broken down into subtasks, maybe for the sake of efficiency. And that's actually what you would see here in this example. So this is taken from a paper by Ferrante et al. And they looked into the behavior of leafcutter ants. They have to collect these leaves, I think, for this like fungus that they're growing. And there's two ways of doing that, right? You could have only generalists. They climb up the tree, cut a leaf, walk down, go all the way to the nest. Or you do actually division of labor and task partitioning. That means you have collectors that just pick up whatever fell down from the tree. And up in the tree, you have another group of ants that just cut leaves like all the time and make sure in the cache, like just beneath the tree, there's always some parts of leaves there for the collectors. And so what they try to do, and I won't give you the full story, but I'm happy to discuss it later. They try to implement that on robots, but actually with a like kind of machine learning approach, actually in this evolutionary approach, to make them figure out themselves how they can distribute these tasks among themselves. And one more thing, the third part here on the left is task switching. That means if you have specialized tasks, like changing from a dropper to a collector comes with a cost, right? You have to climb down the tree, which means you're not efficient in that moment. And that means you should minimize how often you want to switch tasks. So it's actually can be quite challenging. Speaking of challenges, so the environment could be dynamic, right? So whatever worked in the last hour might not work in the next hour. And you might need to reallocate. Even if you found a good allocation of robots to tasks, you might need to rework that later. Load balancing, right? So there might be, well, you always have like supply and demand, and then there might be moments when a certain task is understaffed, for example, and then you want to assign more robots to that at the cost of another task. So how to maintain a balanced distribution, and this partial observability, a big deal in AI, but also in robotics. Like these robots can only locally measure like how many others around me are currently working on what task. It will not have this information about what is everybody doing currently. And can it still make sense of that? And like how noisy will be these decisions if maybe just locally around you there was an imbalance and then you immediately switch. So how can possibly biology help here? The standard model would be the response threshold model that I try to very quickly summarize here. So this is our first equation today, congrats. You can calculate, this is a model from biology, right? So this is how biologists guessed that this might be going on, for example, in social insects. This is a probability of taking up, like starting a certain task. And so you have this function, s to the power of n divided by s to the power of n plus theta to the power of n. And so S would be a stimulus, for example, how many busy robots you see around you or something else, or how many leaves are there in the cache. Theta is a threshold, that's a parameter you want to tweak. And N would be the steepness. So here I've plotted some of these functions for different N. So threshold here is always 1. So if you look on the horizontal axis, 1 is this break-even point because that's theta, and then the steep one would be a high N, and the purple one would be a low N. So you can choose like how aggressively these robots or animals should switch tasks depending on whatever they perceive in that moment. This is obviously not the full story, right? So this is like how, like what's the probability to take up a certain considered task. If you have multiple, you need to like maybe compare different probabilities and so on. And what's also interesting, in swarms you have some heterogeneity there sometimes. So there's not this like one threshold for every ant in the colony. They actually are sampled or seem to be sampled from a distribution. That means some ants would be very aggressive and like sensing like, these are all stupid ants. I have to quickly switch to this other task because otherwise nobody will do it, right? And these other ants that are very relaxed and they're like, yeah, okay, someone will finally do something, right? Like, and they're waiting long until they switch tasks. And if you have a good distribution of these different personalities, then maybe this is fixing already something in terms of robustness in the swarm. So as I said, I'm not giving you the full story, but they used evolutionary computation to like tweak a certain model. And so here's some data. On the top you see like most of the robots actually went to the source, like they were climbing up the tree because the cache was empty. They started to cut leaves and then the cache was filling up and then robots were like switching to the collecting task to pick up these pieces and like if you have everything like working well, then you have a nice distribution of robots between being on top at the source and being below at the nest and cache. Also here, yeah, you see like how the cache fills up, and then there's of course some fluctuations and so on. But if everything works out nicely, then you have a very efficient system, maybe also robust. So it could remove a robot, and maybe they still adapt to that. Interesting, maybe is also like is there like a sweet spot or like a minimum swarm size at which this task specialization would actually emerge? So would you have for very small swarms generalists? And then if you put more and more robots, they figure out that now it makes sense to specialize. That would be an interesting thing to ask here, for example. And this is what we actually do in my own lab. So we use this task allocation problem directly inspired by Ferrante et al. For our turtle bots. We want to use a very special method called minimize surprise to solve this problem. And this is like some early tests in the lab. So we want to use tennis balls. And then if there's no slope, of course, the robot has a hard time. It's also basically blind to push this tennis ball into the nest. But this is, of course, one piece of behavior that we will need to make this happen, what you see here in the simulation, actually with a slope where the robots push things around. So just, yeah, if interested, ask later. Good. That was example one. So now I would want to talk about flocking a bit, and I understand you're well prepared, right? So you've heard already quite a bit about collective motion. So the biological inspiration would be something maybe like this, right? So I have these like sector models with forces of attraction and repelling forces, such as the Cassin model. So I'm just putting kind of arbitrarily some equations here where you have a repulsion if other robots neighboring to you are too close. You try to align in terms of orientation, and if you're a bit out of the swarm, you might be forced or pulled in back by some attraction force. Depending on parameterization, you might see a more like random kind of behavior or like very much aligned behaviors, or more like this milling, for example. And so these models exist, right? And if you want to have flocking robots, be it flocking drones or flocking mobile robots in the lab on wheels, you could just use these equations and implement them on the robots, right? Like, why not? Why not? Maybe one more. There's the Witschek model. This is more like from the physics side, but I think it still counts as a biological model. So you see this position update, which is just a bit boring because that's just using like a velocity vector. And then the heading update has this like fancy way from physics of how to put averages and so on. But it's basically within a certain neighborhood is averaging headings so that everybody like over time hopefully agrees on traveling in a certain direction. And then you will see like these typical behaviors and Tamash is famous for having found this phase transition depending on density and certain parameters and so on. So there's all this stuff out there. Okay, it sounds like an easy job for Swarm Robotics. Just choose your model and implement it on the robots, right? Why not? Problem is, I don't know, is it our robots that are so stupid, or is it that these models from biology are wrong? Who knows, right? It's actually hard for most of our robots to determine the heading of a neighbor. This is in robotics we would call that a state estimation, or like a pose or bearing estimation of your neighbor. So how would you do that? Depends, right? You can maybe put a camera on your robot, and you could like try to look closely, and if you know a bit like how this robot looks like, you can maybe tell, the front is on that side, so probably it's going in the same direction as I am. But this is actually hard to detect and calculate. You could try to like use communication, maybe you have a compass and you can send your compass reading, but that's already kind of like faking it a bit. It's not so easy, right? And imagine you don't have a camera, and then how can you really do that? It's amazing actually that these birds, for example, can do it. I mean, they have like more cognition than most of our robots, and so most of the time quite good eyes. But this is a problem, right? So people have tried doing this on real robots, and they find like, actually it doesn't really work, right? I'm not sure if this tells anything about biology, so I'm not saying this is informing biology necessarily, but might be. Also, our robots are not very agile, right? These differential drive robots, they turn on the spot, and it's very different from, like, I mean, imagine birds flying. And then also usually we have not infinite space, so we put them into the lab, and then there's wall effects, and that's making things a bit difficult. By the way, I mean, there are solutions out there. I'm not saying this is how we should do it, but to inspire you a bit. In aviation, right, they figured out this is actually a problem. Imagine there's a pilot, and maybe they don't have all the technology of today in their airplane. And then you see an airplane in front of you. And you're wondering, is it going this way or that way, right? And that's an important piece of information, right? So as I understand, I'm not a pilot, they put these lights. I'm not sure if green and red is really clever, given that there's a high percentage in males that are colorblind, but okay. So if you see a green and a red light, then this airplane is facing you. If you see these white like tail lights, then you might be safe, still depending on the speed of this airplane. So it sounds like we would need something like that, or like what can we really do? And this is indicating, this is actually a picture I stole from David's paper. This is indicating wall effects, right? So these birds, they just fly around. Usually there's not so many walls up in the air. Our robots usually would at some time run into walls and then struggle a bit of like making sense of that, and then awkwardly navigating around to not run into each other and try to align again. So all of this is difficult, and we cannot just take some of these famous models. But again, so in David's work, we were inspired by a vision-based model that goes back to these guys. So you know Pavel also maybe has shown you a bit about that. So there's the idea that you don't really need to know headings, like where these other neighbors are going to. You only look into where are they around you and basically how far away. And then because just like vision does most of this job, that's something that is far away, would like only count as a little weight on whatever you consider and calculate here, while something that is really close, you would put a high weight basically on that, because that would be a big black bar in your calculations. And so this is what David and his team implemented, and you get this really smooth robot flocking behavior with vision. That's already a lot of computation actually on board. So great that we can actually do that. And these robots would align and move together. Still bio-inspired, because this vision-based model, I think, was inspired by fish behavior, but not these classical models. They turn out to be actually a bit awkward and tricky to implement on robots, right? So the story here would be, maybe it's not always so easy to just like steal something from biology and just put it on the robots and it works, right? So this is unfortunately not always how it works. So one last thing would be this idea. There are a few papers out there which communicate this like lesson of less is more sometimes in biology. Here indicated by a piece of architecture from Mies van der Rohe. Not sure if you want to live there, but why not, right? So in the middle of Berlin, if you have this house, I don't know, you make your choice. So what is this less is more? So we're talking about collective decision making, right? You have a swarm of animals or robots, and they're presented different options, a number of options n. They come with different qualities, and the swarm is supposed to choose what is the best option right now. We assume they have not that knowledge, so they need to pick one, go there, explore, find out the quality, come back, communicate to others, and then over time communicate and agree on one of the options. And this might also be dynamic, that whatever was best yesterday might not be best today. And then in that sense, they have to adapt and reconsider their previous decision. So this is what we call best of n, many options, different qualities. We assume these robots are quite dumb. They have a limited amount of memory, no prior knowledge, and only local communication. And in this paper I'm referring to here, this is Talamali et al. They used the so-called voter model, which is you take the opinion from one of your neighbors. This is not how you should make your political decisions, by the way. So you pick one random neighbor and just copy their opinion, right? Actually, it sounds stupid, but it works in animals and possibly and for sure in robots. And then they also use some cross inhibition, so someone who's really convinced of their option, they can also like stop others from going to other options. So they randomly interact. Imagine these robots moving around like mostly randomly. So you run into different neighbors every now and then. They compare their site qualities and then they update just based on what they learn. So they actually trust these other robots and then they try to quickly adapt and find what's the best option. And then this counterintuitive finding that Talamali et al. Found here was that if you reduce the communication range, so you reduce the number of neighbors that you're considering, you sometimes get a better adaptation. So the robot swarm faster adapts to this new situation where actually an option that was suboptimal before has become recently the best. And that's a known situation from biology. So in that sense, it's a biological inspiration. And it's a beautiful result, I think, because this is really something an engineer might not have really thought of. I mean, it's always difficult to argue, like, what can a person possibly think of? But this is by doing less, like communicating less, having less information, basically, doing better. So these robots would have fewer links, so there's like less chances of forming like these bigger echo chambers, and then there might be an informed minority, like these guys that explored this new best site already, and then maybe try to convince others. So this might work unexpectedly better then. So this is like the situation, again, from the same paper, not my own work. So this is this little kilobot, this tiny robot, and then they run around. These circles represent these different options, different sites. They go there, then they are communicated a quality, and they constantly talk to each other, but only within a certain range, a small range, to tell like, hey, red is great, go to red, or whatever other color. These colors don't mean anything here. Don't go crazy yet. So they measure these qualities, talk to each other, and then collectively agree and hopefully find a consensus on what's best. And they would do this in a dynamic setup. So you can tell it a bit from the top left diagram. This is over time, 80 minutes of an experiment, where in the beginning, red is the best option, then this switches, and blue is getting the best option, and then that switches again, and then green is the best option. And they're measuring here, like for different methods, how quickly do these robots adapt to this new situation? Like how long does it take them to get out of this like potential lock-in state? Everybody agreed on red is great, right? To understand like, no, this actually changed now and we have to switch to something else. So it might be that an option disappears. It might be that a quality like swaps, so quickly changes, and this is then what you see is happening in the arena. Just to give you like some data so that you do not only have to take my word, this is a bit difficult to understand maybe. So on the vertical axis in both of these plots, you see communication range. So if you move there to smaller values, this would like reduce the amount of information because you have less neighbors. And at the same time, you see here on the horizontal axis, like with bigger and bigger swarms, I think this is simulations, if I remember correctly. You have bigger and bigger swarms. And then you see in the black color, this is how well they adapt, like how fast they were able to adapt. And you see that this is getting smaller and smaller areas with bigger and bigger swarms towards the lower part. That means for smaller amount of, for smaller communication ranges. And if you think about it for a while, this is really not intuitive, that basically less information has potential to inform you better or to make it easier to accept that there's like new updated information that you might need to pay attention to, right? Can also talk about that in a bit. So to conclude, I just want to like show you a few possible futures of swarm robotics. I thought like, I just include this slide also because, I mean, since at least 2 or 3 years, it's unavoidable to also think in that direction. So people, like most of these swarms that are used nowadays in military applications are remote controlled, but we're getting there that they get more and more autonomous. So I will not really talk too much about that now, but just that I have that here, and if you want to discuss, we can do that. And it's a special moment in like the history of swarm robotics that this is happening right now. Rather scary, and also we as a scientific community have to deal with that somehow. Some better examples would be, for example, this is or used to be a startup from the Karlsruhe area with whom I worked a little bit. This is I call it autonomous hangars. They build these bags for a warehouse, and they have motors, sensors, compute. And in this startup, they wanted to go really crazy. They thought we can build 1 million of these hangars in one warehouse. And that's when they started to think like, okay, there will be bottlenecks in communication. So we should look into how can you decentralize the system, how can you maybe get inspired from biology. And they actually successfully sold this technology to a big company in logistics from Austria. Then this is from my own lab. We have this EU project, EU-funded project Chronopilot, where we go a little bit crazy about looking into human-swarm interaction with a focus actually on human subjective time perception. Not sure if time is already stretching on your mind. It might be if you're bored, if you're super excited, then you can't tell that we're already reaching the end of this lecture. And we are looking into like what's the impact of robots or robot swarms that you're controlling, partially at least, on a human operator in terms of time perception, but also other things. So we do some physiological measurements, and then we try to do a machine learning based time series analysis of this physio data to classify and understand like how this human operator feels in that moment, and then maybe also adapt the robot behaviors to that. So this is our take on how can you look into human swarm interaction, and hopefully make a useful contribution there. And then you find, of course, like ideas of how you could use swarm robotics in farming, like precision farming. I think this is now I don't remember, is it an American or an Australian company? Often, they call it swarm, but then if you look into it, it doesn't really obey our definition of swarm, but you have many of these devices, and if they're autonomous and they at least cooperate somehow, you can imagine that you can also put maybe robotics or swarm robotics to a good use in a farming setting. One more example is this. This is from an actual paper by colleagues from Croatia. This is monitoring underwater environments. So you would have a heterogeneous swarm with some like swimming up there on the surface. And then you have these kind of like buoys or like submerged devices that can dive down and then also come back up, and they can measure certain water quality features and so on, and do that in a distributed way and hopefully also in a relatively cheap way to measure like any distributed natural phenomenon. And my last example would be then a bit more down to earth. So I told you there's SLAM, this problem in robotics, like you put a robot or a swarm of robots into an environment they've never seen before, and then how can they cleverly explore this world and also at the same time localize themselves so that they can answer this question, where are you now and how could you possibly get out? And at the same time also do a map. And if you mention you do that in a collective setting, they could maybe share their little maps that they've already drawn. And so there's many options there. And this research is also just starting. How can you do that in an efficient way? And hopefully you trust me that this is really a thing in robotics and a useful challenge to take. Yeah, so back to my team. I mean, I've shown you a few things. So you know, Brandov is building the sailboat, and maybe you paid attention and you saw that Till and JK are working on these human swarm interaction scenarios. And there's many other things going on that I didn't tell you about today. So yeah, look it up. We are writing all these papers. Not sure how enjoyable they are to read, but you have chances to look a bit into that. Good. So we still have some time for questions, I guess. Thank you so much for your attention. And now I'm ready to take questions.